How do you evaluate unsupervised learning models without labeled data? Imagine trying to judge a painting without knowing what it's supposed to depict. That's similar to evaluating models that learn from data without labels. In the world of machine learning, unsupervised learning is all about finding patterns and structures in data that isn't labeled. But how do we know if these models are doing a good job? That's what we're here to explore. Since there are no labels or ground truth, traditional accuracy measures don't work. Instead, we look at how well the model organizes or groups the data. One common way is to use internal validation metrics. These metrics analyze the data points and the clusters or patterns the model creates, all based on the data itself. For example, the silhouette score measures how similar each data point is to its own group compared to other groups. A higher score means the points are tightly grouped and well separated from other groups. Another metric is the within-cluster sum of squares, sometimes called inertia. This sums up the squared distances between points and their cluster centers. The lower this number, the more compact the clusters. Then there's the Calinski-Harabasz index, which compares how spread out the clusters are from each other versus how tight they are internally. Higher values suggest clearer, more distinct groups. The Davies-Bouldin index looks at how similar each cluster is to its most similar neighbor, with lower scores indicating better separation. Sometimes, if you have partial labels or some idea of the groups, you can compare your clusters to these known labels. External validation metrics like the adjusted RAND index or normalized mutual information help here. They measure how much your model's groupings match the known categories, giving you a sense of how meaningful your clusters are. Another way to check your model is to see if the results are stable. If you run the model multiple times or on different parts of the data, do you get similar groupings? Consistent results suggest the model is capturing real patterns, not just random noise. Visual tools like scatter plots or dimensionality reduction techniques can also help you see the clusters. When you understand the data's context, you can judge whether the groupings make sense for your specific problem. In practical applications like text generation or image creation, evaluation often involves seeing if the patterns learned improve the system's performance. For example, does the model help generate more coherent text or better images? If it does, that's a good sign it's capturing useful structures. Since unsupervised learning doesn't have labels, evaluating it is more about understanding the quality of the patterns and how useful they are. Combining internal metrics, stability checks, domain knowledge, and application results gives the clearest picture. In the end, it's about making sure the model's groupings or patterns are meaningful and help you achieve your goals. That's how you evaluate unsupervised learning models without labeled data.